Let's look into something called as Lami's theorem. So this is a theorem, it pops up when we have three force systems that have balanced each other out. Let me explain what that means. Say you have a point, right? And that point is suspended in air. Okay. So that point is suspended in air. So of course, in day-to-day life, things aren't suspended in air. They are held in air by quite a few ropes or things like that, or any other force, say non-contact force also, they can be suspended. So if it's suspended with three forces like this, that is, if this setup, that very setup, right, if you have three forces acting on it, it can be in any direction. And if this is at rest, okay, so this object is at rest. I meant this is okay. If this is at rest, then we can apply your Lami's theorem. So that's when you can apply your Lami's theorem. Now, why is that we are learning this? Well, this is pretty much applicable in things like stable structure like cranes and suspension bridges. So bridges and cranes have to be stable, right? They can't move around. So that's where it's applied. Okay, let's look at the statement. It states that for three forces that are in equilibrium means they are compensating each other. They are cancelling each other out. So the net force is basically zero. That's what it means. So basically this is happening because the net force of this system is equal to zero. That's your state of equilibrium. If this is happening, then the ratio of each force's magnitude to the sine of the angle opposite to it, actually is a mistake. Opposite to it is constant. So let me explain it this way. So we have these three things, right? So if you happen to have the angles to be say alpha, beta, and I think, okay, I'm not taken any. So I'll use this itself, I guess. If we happen to take this up, and if this is say alpha and say beta and theta, and say this is F1, F2 and F3, then what the theorem is telling is if I take F1 by sine of angle opposite to it, that is alpha, this will be equal to F2 and the angle opposite to it is beta, so sine beta, and this is equal to F3 and the angle opposite to is theta. This ratios will be equal to each other. That's it. As simple as that. Okay guys, that looks like what your law of sine that comes from your vector chapter. I hope you guys remember. Now, how do you prove it? So it's quite simple actually. So we rearrange the vectors. Okay, so if we rearrange the vectors, then we are getting this diagram. So I need to copy this again to explain further. This works if your vectors are, actually in equilibrium. If not, this will not work. At least the proof, it won't be that obvious. Okay, so I'll call this as say alpha, right? So it's the angle between the tail of green and red vector. Do you guys agree? So green is over here. I'll do this actually now. I'll copy the green again. I'm just copying the green, right? And I'm placing over here. Now, if I happen to extend this line in this manner, what is this angle? Sorry, actually this angle. What is this angle? How much is this angle? This is parallel to this. This has to be alpha because of corresponding angles. You guys agree? Then how much will this be? 180 minus alpha. That will be 180 minus alpha. So this was alpha. This became 180 minus alpha. It is the opposite angle to the blue. Can you see that? This is blue. Opposite to that is this particular angle, and that is 180 minus alpha. Similarly, I'll be able to prove this will be 180 minus whatever this angle is, and so on and so forth. Okay. So let me actually standardize this. Let's have a clear picture. So mathematical proof will look like this. So that should be a first diagram, and we should label it. Say I'll label this as F1 and say theta, F2, F1, and say this is F2, and opposite to that is say alpha, and this I'll call it as F3, and we can call this as beta. Okay. Now what we have to do next is create a triangle in this manner, right? By shifting the vectors around. So we'll create a triangle. So that's part of your proof. Now you understand that this has to be 180. Remember, this is opposite to blue. So this is F1, this is F2, and this is F3. Opposite to F1 is theta. So this has to be 180 minus theta. Opposite to green is alpha. So this has to be 180 minus alpha. And this is opposite of F3. That's beta. So this is 180 minus beta. Right? And you have a triangle. So I can name it as a triangle. So the proof will go like this. Right? Let's consider three forces which are in equilibrium. Actually, I should be writing in this manner. That. So consider a point O under the equilibrium of three concurrent forces. What are they? For us, it is F1, F2, and F3. Then we'll talk about the angles also. Let theta, alpha, and beta be the angles between, I'm off a screen over here a bit, angles between, you guys can complete that. Theta is between F2 and F3, comma, so on and so forth, respectively. That word we need to use. Then from figure 2, right? So that's our figure 2. It's clear that the three forces can be represented with sides of triangle ABC. Now, okay, so applying the law of sines to triangle ABC. Guys, there's something called as law of sines. If you guys don't remember or not studied this, there's a separate proof for this. So you guys can have a look at that. So sine F1 sine of something, this will be equal to F2 sine of something, and this is equal to F3 sine of something. So F1 is opposite to F1 is, this is F1, right? 180 minus theta, and then alpha and beta, theta, alpha and beta. 180 minus theta and 180 minus beta. So you know that sine 180 minus anything will give us the same value back. So F1 by sine theta is equal to F2 by sine alpha is equal to F3 by sine beta. Right, guys? So that would be your Lami's theorem. Please write the statement and then the proof. So look into law of sine. It's actually simple. Science proof. So that it makes sense, you know.